Okay. Good morning, students. During last lecture, we discussed about the strict alteration method as a solution for mutual exclusion. Okay. In the strict alteration method, if you remember, we had two algorithms. Okay, we had two algorithms. Okay. Both the algorithms will be executed by two different processes. Okay. So here for every process, we need a separate algorithm. That means the variable of here, the variable should be different. Okay. So that was a disadvantage here. And only two processes can execute the can compare to use the critical section at a time. Okay. Then we have another solution for mutual exclusion to attain the mutual exclusion. To achieve the mutual exclusion, we have another problem which is called Peterson solution. Okay. Peterson solution suggests a single algorithm. Okay. But this can also be used by two processes. Okay. But what is the disadvantage of Peterson solution over strict alteration? Here, there is no separate independent variable which will denote the process ID. Okay, so there is no need for change in the algorithm. There is a single algorithm which should be executed by all the processes whichever wants to use the critical section. Okay, students, am I audible? My voice is clear.
Yes, ma'am, we audible.
Students, some of the students I'm admitting now. Okay, everybody should be there on time for lectures. Remember, okay. So everybody should be on time for lecture. Okay, lecture and also practicals. Okay. Okay. Now, what Peterson solution says, here there are two processes. Look at here. Look at here. I will explain the algorithm also. Okay. There are two processes. Okay. We assume that those processes are P0 and P1. P0 and P1. Okay. And initially interested processor, or otherwise we can consider this one. Assume that there is a variable called interested process. Okay, it is an array variable. Okay, interested process is an array variable. Now this process can be 0 or 1 depending on which process is trying to use the critical section. That means which process is executing the program currently. Okay. So this process can be 0 or 1. Okay. 0 denotes process 0, 1 denotes process 1. Okay. Initially, we are assumed that interested process equal to, it is a Boolean variable. So interested process initially for process 0 false and process 1 is also false. I stroke out. Okay, so that you just ignore. Okay, initially P0 and P1 both will be false. That means both the processors are initially in the non-interested state. That means both are not attempt to execute the code. Okay, so that we will keep as a default value for P0 and P1. That means default value of interested process. Okay, interested process may be interested 1 or interested 0, whatever it is. Initial value of the variable is FF. Why FF? F denotes false. That means it is a Boolean variable. Okay. Now first we assume that P0 process initiating the execution. Okay. Now come to algorithm. There is an integer called other. Other is a name of the integer. It's a variable name. Okay. And other equal to, what is other? Other equal to 1 minus process. Now what we assumed that process P0, please listen. Process P0 started the execution first. Okay. Now what is process here? I said if process P0 started, then interested process equal to interested of 0. Okay, that 0 denotes process 0. Okay. So here other equal to 1 minus process. What is process currently? Currently process is 0, isn't it? How come 0? We assumed that initially process P0 is started to execute the process. Okay. So this process is what? It's an integer, that is 0. Okay. So 1 minus 0 equal to what? 1 here. Okay. So other, automatically it is like other equal to 1. Other equal to 1 means what is the other process? Other process is process 1, no? So you are getting other equal to 1 minus 0 equal to 1. That means which process is other process? Process P1. That is denoted by 1 here. Getting it?
And some students are
Students?
still in the waiting room.
Students, please join for the lecture on time. On time plus please you have to join. Okay. So first we have taken two processes P0, P1. Okay. Interested process is a variable which is a Boolean variable. Okay. Here the process can be either 0 or 1. Okay. That 0 denotes the process equal to 0 denotes process P0. Process equal to 1 denotes process P1. Okay. Initially, we assumed that interested of process for both the processes P0 also false, P0, P1 both are false. Okay. So now what is the first one? First, when P0 executes, other will be 1. Okay, how other will be 1? Other equal to 1 minus process. What is process now? 0. Okay, because process P0 initiated the execution. Okay, so process equal to 0, 1 minus 0 equal to 1. Okay, so then what is other? Other is nothing but to denote the other process which is not interested now. Okay, so that other equal to what now? 1. Remember, that's what here I have given, other equal to 1. That denotes what? P1. That denotes P1. Okay. And then turn equal to process. Turn is another variable. Turn equal to process. Now turn equal to process means currently process is 0, right? Process is 0. Why? Because P0 initiated the execution. Okay. So turn equal to 0. Here process is what? Integer. So it should be either 0 or 1. But here it is 0. So turn equal to 0. Okay. Turn equal to 0. This 0 denotes, wherever 0 comes, that denotes the process 0. Wherever 1 comes, that denotes process 1. Okay. Now what is the whose turn? Turn of P0. That is integer 0. Okay. Now look at the condition. While interested other. Now what is other is what? Other is 1, no? Here, look at here, other equal to 1. Okay. So interested of other equal to true. Is this correct? Is this true or false? Interested of other. So currently interested of other equal to what? False. Because we initialized both false. Okay. So interested of other is false. But here what it is saying, interested of other equal to true, that means this condition fails. Okay, this condition is false. Okay, false. There is another condition conjected with and. What is that? Turn equal to process. Okay, that means turn equal to 0. That's correct. Okay, so this is true. Turn equal to process. Here, look at here, turn equal to 0. Okay. So what is process now? Process equal to 0, no? So turn equal to 0 will become true. So in while loop, one condition is false. One condition became false. Another became true. So look at here. False and true became false. Isn't it? So look at here one more thing. As I said before, this is what? This is This while loop does not have body. So we terminated here. Okay. When it will come out of this loop, out of this line, when the condition false. Okay. Here the condition false. Here the condition false. How it came false? How it became false? Because interested of other equal to true, but actually it is false. Interested of other is actually false. So this condition become false. Okay. And one more condition, turn equal to process, turn equal to 0. Yes, turn equal to now 0. So this condition true. So false and true, finally it became what? False. Okay, you know AND operator. So when the condition false, definitely it will come into the next line. Okay. Next line is a critical section. Next critical section. That means currently P0 entered inside the critical region or critical section. Okay. I put this lines that denotes, assume that process P0 is currently in critical section. Okay, currently in critical section. So it will take some time to execute the critical section code segment. Okay. Now currently the process is in critical section. Which process? Process 0. Okay. But remember, this process P0 did not come out of the critical section. When it comes out of the critical section only, this line will be executed. Okay, so till now, process P0 did not execute this statement because it did not come out of the critical section. Okay. When the process P0 is in critical section, when process P0 currently in critical section, assume that everywhere what we are trying to prove, all these algorithm, only one process at a time in a critical section. Okay. So that is what we have to prove, whether the algorithm satisfies that it is allowing only one process at a time in a critical section or not. Okay. So that here we passed and then we are coming to process P1. Assume that process P0 currently it is in critical section. That time process P1 start to execute this. Starts to execute this. That time what will happen? Other equal to 1 minus process. Now what is process? Now what is process? Now process is P1. Okay. So other equal to 1 minus 1. Why process equal to 1? Because currently we have taken the process what? P1. Okay. What about P0? P0 it is there in a critical section now. Okay. P1 starts to execute the code. It will execute other equal to 1 minus process. Now process equal to what? 1. Process equal to 1 because process denotes the current process. Okay. Who's currently executing the code. So 1 minus 1 will be 0, which makes other equal to 0. That is correct, no? Other process. When process 1 is inside, then other process will be P0, no? So other equal to 0. That other equal to 0 denotes what? Other equal to 0 denotes P0. Look at this line. Other equal to 0 means P0. Okay. Interested process equal to true. Which is interested process? So interested of 1. Now currently process interested of 1 equal to true. Okay. Interested process equal to true now. Okay. Which is nothing but here we are making P1 true. It was initially false, no? Now we are making this as true. Okay. This is clear. Interested of process is now what is process? Process 1. So interested of 1, which is P1 equal to true. And then turn equal to process. Now turn equal to 1. Okay, turn equal to 1 because turn equal to process. What is process? Process equal to 1. So turn equal to 1. Now turn equal to 1. Look at here. Turn equal to 1. That denotes this is a turn of process 1. The 1 denotes P1. Okay, so this is a turn of process 1. Okay, what is the value of the turn variable? Turn equal to 1. Then it is executing, who is process P1. Remember, process P1 executing while interested other equal to true. Interested of other is what now? Interested of other will be true. Yes, this condition is true. Okay. Interested of what? Interested of now other what? It is 0. Interested of 0. Interested of 0 equal to true. Yes, it is true. And turn equal to process. Turn equal to process means turn equal to 1. Okay, because current process is 1. See, look at here, turn equal to 1. Okay, so turn equal to process means turn equal to 1. This is also true. When both the conditions are true, finally it will be true. Okay. So when it is true, the while loop is true. This is busy wait while loop. So it is terminated here. When it is true, again, it will not come to next statement. It will be spin inside the loop itself. Okay. So again, it will come here. It will check both the variables again, and again. It will keep on check the variables. That means here what you have to know, P1 is not allowed to go inside the critical section because already P0 is there. As P0 already there, P1 should not be allowed to go inside the critical section. So here there is a busy wait. Here there is a busy wait. Okay. Now assume that our process P0, now it is currently in critical section, no? It is completed the execution of critical section. It is exiting from the critical section. Immediately after it exits from the critical section, it has to execute this statement. Interested of process equal to false. Now what interested of process? Interested of process is nothing but currently process. Here this is executed by P0. Okay. So interested of P0 equal to false. Okay. Because before it enters, P0 enters, it made the P0 true and then went inside. So when it is inside, this was true. P0 was true. Okay. Now after it came out, it is making P0 equal to false. The moment it makes P0 equal to false, what will happen? Here, this lock, this busy wait will be released because this will become, the first condition will become false. This is false, the second condition will be always true. Then it will come inside, the P1 will come inside the critical section and it will start to execute the critical section. And upon executing the critical section, even our P1 will also reset the interested of process equal to false. Okay. So this way the algorithm will work. Advantage of this algorithm when comparing with the strict alteration is, in strict alteration, what was the limitation, disadvantage? There are different algorithms for different processes, and also only two processes can execute. Can be that algorithm is designed to execute only by two processes. Okay. But here also this algorithm is designed to execute by two processes only. How I am saying? Because here the process value, the other will be 1 minus process. That means other can be either 0 or 1. Even turn equal to either 0 or 1. That means only two processes. Here we are considering only two processes. Okay. But then what is the advantage of Peterson solution over strict alteration? Strict alteration needed different algorithms for different processes. But Peterson solution reduced that. That means that overcame that disadvantage. It made a single program, that means single algorithm, which will be used by all the processes which wants to use the critical section. But anyway, algorithm is designed that at a time only two processes. One will be inside the critical section, another one will be in waiting state. Okay. So that is the difference between strict alteration and Peterson algorithm. Okay. Next we have another algorithm, but in your textbook continuation of this that they have given after discuss about some other chapters. But okay, now if you see this Semaphore also, Semaphore is another solution for mutual exclusion. To enforce the mutual exclusion, you can use the Semaphore also. We will see what is Semaphore. Okay, I'll just close this. If you want to take the snap of this, you can take. But anyway, this I will upload in the Teams. Okay. Now we will discuss about a semaphore. Okay. Now what is semaphore? Semaphore is a variable. Just the name is like that, but semaphore is what? It is just a variable. Okay, it is a integer variable. But the semaphore can be used, but this is not like other variables. This is some special variable which will have fixed values. Okay, some range of values only it may have. Okay, that is called a semaphore. Okay. Now the semaphore is in two types, binary semaphore and counting semaphore. Binary semaphore is also called as mutex. Binary semaphore is also called a mutex because it is a solution to achieve mutual exclusion. Okay, that's why it is also called a mutex, or it can be called binary semaphore. But this counting semaphore, no, it is not a solution for mutual exclusion. Okay, but it is solution for something else. We will discuss that. Okay, but remember there are two types of semaphore. Okay, one is binary semaphore, or another name for the binary semaphore is mutex. Okay, we have another semaphore which is called counting semaphore. But counting semaphore is not the solution for mutual exclusion. Okay. But binary semaphore is yes. That's why we are studying semaphore under this, because we are studying about the mutual exclusion, how to design, how to achieve the mutual exclusion. This is one of the ways. This is very best way to enforce the mutual exclusion. Okay. Students, are you all hearing, listening? Everybody is listening?
Yes.
Okay. Now, what is this? First, we will see binary semaphore. This is the algorithm. The process will be executed. Okay. Here they have called they used two functions, which is called wait and signal. Wait and signal. So the binary semaphore will use always wait and signal, two built-in functions. Okay. But you have to understand what it is. That's why it is given what is wait. Wait is this one. Signal, what is the definition of signal? That means this is a calling of function. Okay. So when this function has been called, what will be executed? This will be executed. Okay. So this is a signal function. This is wait function. This is signal function. Okay. Assume that there is a process entering inside it wants to enter inside the critical section. So first, it has to execute the wait of yes. Okay. What actually wait of yes may it will execute? Here comes wait of yes. We have to initialize the value for yes, no? We have to initialize the value for yes. Okay. We initialized yes equal to 1 because this is a binary semaphore. So yes can be, yes is nothing but semaphore. Okay. So the yes can be either 0 or 1. Why? Because we are seeing about the binary semaphore. So semaphore can have either 0 or 1. Okay. Assume that semaphore is starting by taking the initial value 1. Okay. So one process came inside this. Assume that that is process 0, P0. So to enter inside the critical section, it has to execute this, isn't it? So it is executing. What it is executing? This is a function call, so control will come here. Okay. While s less than or equal to 0. Is a condition true or false? What we assumed? We assume s equal to 1. Okay, the s is nothing but semaphore. Okay. So 1 less than or equal to 0. Okay, this condition false, isn't it? The condition false. Okay, 1 less than or equal to 0. So the condition will be false. So it will come here. If it false, it will come here and it will decrement to s equal to 0. Okay. Now what? S is equal to s minus 1. What is the value of s? 1. 1 minus 1 equal to 0. Now currently s value equal to 0. Who made the s value equal to 0? P0, process 0. Okay. Now making, after executing this, process will execute because the process P0 could execute this successfully. Okay. So by making s value equal to 0, the process will enter inside the critical section. Process will enter inside the critical section. Okay. Now currently the process P0 is inside the critical section. Okay. Assume that there is another process. When assume the process P0 currently in critical section, it did not come out. Okay. Assume that it is a multi-processing system. So another process is executing the same code. It is seeing weight of 0. So it will come here. Now this is process 1. Okay, P1. Weight of s. While you know what is the current value of s? S equal to 0. So s less than or equal to 0. Yes, the condition true. When condition true, it will not come to next line. Again, it is a busy loop. See the semicolon. Again, it will see whether s is less than or equal to 0. Again, it will see. Because s equal to 0 now. Okay. Now what it shows, when the process P0 inside the critical section, process P1 could not enter inside the critical section. Okay. Then when the process P1 will enter inside the critical section, come to process P0. P0, assume process P0, now it executed the critical section. It is coming to next line. Upon executing, after executing the critical section, it will come to signal of s. What is signal of s here? Signal of s is simply incrementing the semaphore variable. Okay. Now currently semaphore variable is 0, no? 0 plus 1 equal to 1. Now currently s equal to 1. Who made s equal to 1? Our process P0. Okay. So the moment process P0 made s equal to 1, here process P1, it is in a busy wait, no? It is in spin lock. Okay. This will be released. This condition will be false. Because s became what now? 1. So s less than or equal to 0 became false. It will come here, s equal to s minus 1, which is now process P1 is making s equal to 0. Making s equal to 0, process P1 will go inside the critical section. Okay. Now currently who's inside the critical section? Process P1 is inside the critical section. Okay. Assume now currently process P1 is inside the critical section. You should only remember the value of the s. Value of s is currently 0. Who made 0? Our process P1 only. Before entering inside the critical section, it made s equal to 0. Okay. Assume that process P3 is coming. Process P3 is currently P1 is P2 is coming. Currently P1 is inside the critical section. Okay. Assume process P2 is coming. Process P2. Process P2 execute the same thing. it has to, it also wants to enter inside the critical section, but before entering inside the critical section, process P2 should execute wait of S function. It will come here, S value equal to 0. The condition will be true. So again, it is in a busy wait. It cannot come to the next line. Again and again and again, it will be seen. So now process P2 is in busy waiting. That time, who is inside the critical section? P1. P1 is currently inside the critical section. Assume process P1 executing the critical section, and then it is coming to next line. In the next line, a function call of signal. So it will come here. And process P1 now increment S value to 1. Okay. Now what is current S value? S value equal to 1. What our P2 is doing? P2 is currently in the busy wait. Okay. So P2 now this P1 made S equal to 1. Then immediately here the P2 can come inside the next statement. Why? Because S equal to 1, the condition false. When condition false, you can come inside. S equal to S minus 1, that means now P2 is making S equal to 0. P2 is making S equal to 0, and then successfully it will go inside the critical section. Like this, the same code can be executed by any number of processes, through which we overcame the disadvantage of Peterson process. Peterson solution. In Peterson solution and even strict alteration, only 2 processes were allowed to be to use the algorithm at a time. The algorithm was designed like that. Okay. But here, any number of processes can come and execute the same algorithm. But in only one process will be there in the critical section at a time. Okay. So this is binary semaphore. Okay. So why binary semaphore? Because S value can be 0 or 1, not anything else. You may ask, ma'am, S is some one variable. Why they have to put a special value for that variable? See, when we are generally calling variable, no, variable may have varying values. Okay. But here the semaphore is a special variable which can have either 0 or 1 if it is used as binary or mutex semaphore. Underline, if it is used for binary or mutex semaphore, this S variable, no, semaphore variable can have either 0 or 1. That's why it is called a binary semaphore. When semaphore is used as binary semaphore, that could be solution for mutual exclusion. You can achieve mutual exclusion using that semaphore. Okay. What is counting semaphore? Counting semaphore is like the semaphore. Here also we will use variable, but variable value is not necessarily it should be 0 or 1. It can be anything, any integer value. Okay. But what is the use of that? Now, during the COVID and all, for example, in cinema hall, only 50% of the people can be allowed. For example, assume that 100 seats are there. Okay. 100 seats में 50% मतलब क्या है? 50% मतलब 50 seats. Of course. So how can they restrict the seats to 50? Of course, in cinemas and all, it's not a proper example because by counting the ticket, we can find. Assume that there is a mall. Okay. Inside the mall, government is saying that only 50% of capacity should be allowed. Who can count here? 50% only people are there at any point of time. Inside the mall, only 50% of people are there or not. How we can confirm? Of course, there is a way when they are entering itself, we have to start to count. But if you do that in automated way, how can you do? You can use the counting semaphore. You can keep the counting semaphore. For example, assume that only 100 people, or we will take small number, only 10 people can be allowed to some place at a time, only 10. Okay. At that time, what we will do, we will use the semaphore value as 10. We will set the semaphore value as 10. Okay, please listen. We will set the semaphore value as 10. Why we are setting 10? Assume only 10 people can be, maximum 10 people can be inside one particular shop. Okay. So for that, we are assuming that initial value of semaphore equal to 10. Okay. If 100 people only allowed, you can keep S equal to 100. 200 people can be allowed, you can keep S equal to 200. Okay. Just for simplicity, we have taken 10. Okay. Okay. First person enters. So when he enters, the weight of S will be executed. Okay. So that will come here. Weight of S equal to now what? While S less than or equal to 0. While S less than or equal to 0. This condition true. Because assume S value 10. So 10 less than or equal to 0. No condition false. So it will come inside. S equal to S minus 1. Now S value equal to 9. Okay. 10 minus 1, which is nothing but 9. Remember, currently S value 9. Okay. Critical section. That means the person is inside the shop currently. He entered inside the shop. Okay. Okay. Another person comes. For him also, he has to execute this, isn't it? He has to execute this. Now S value 9. 9 less than or equal to 0. Yes. It is false. Okay. 9 less than or equal to condition false. If condition false, it will come inside S equal to S minus 1, which means what? Currently S value equal to 8, isn't it? That person also successfully enter inside the shop. See here, the shop, you should not say critical section. Okay, critical section means only one person at a time. Assume that this is a shop. Critical section we are assuming as shop. Okay, so second person entered. He is also currently inside the shop. Another person comes executing this. Semaphore value will be 7. Then another person 6. Another person 5, 4, 3, 2, 1. Okay. Now semaphore value is 1 currently. There are 10 people inside the shop. Okay. 10 people inside the shop. When last person entered, he made semaphore value equal to 0. Okay. He had the value 1. So 1 minus 1 equal to 0 he made. Okay. Now currently 10 people are inside. 11th person comes. 11th person comes. He is also executing wait. So he has to execute this. But he cannot make this condition false. The condition is true because S equal to 0 currently. 0 less than or equal to 0, yes, true. He cannot execute the next statement. Again, yes less than or equal to 0, yes, 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 yes. So the 11th person cannot go inside the shop. But when he can go inside the shop, there is, assume that first person who entered inside the shop, he completed his shopping and he's coming out. When he's coming out, he has to execute signal. Okay. So he's coming here. Okay. So now currently, S equal to 0. He's making S equal to 1. Okay. That means one person came out. Now currently how many persons? 9 persons. Okay. Now one person is waiting to enter. Okay. The last person who came out made S value equal to 1. Okay. So the person who's currently waiting here, the 11th person, he will now the condition, because 1 less than or equal to 0, this condition will be false. He will come and execute this. He can go inside the critical section. One person left, new person entered. But now also how many people? How many people? 10 people. Assume that one by one there are 3 people left. So here the value will be 3. Then 3 more people will be allowed to go inside. Okay. So like this, counting semaphore will work. Is this clear, students? Are you all listening?
Yes, ma'am. Yes, ma'am.
Why? Volume is very low. Everybody understood?
Ma'am,
Prathamesh and Saima. Prathamesh and Saima, why are you joining now? I'm going to end the lecture. Now you're joining. Why? Prathamesh and Saima. Prathamesh, you're there in the meeting, no? I'm asking to you only.
Yes, ma'am, there was
Prathamesh.
a net issue, so I log
So
out.
you joined already? Or now only you're joining, no, for lecture? For my lecture.
No, joined, but there was a net issue, ma'am.
Then you got disconnected.
Yes.
Saima, what about you?
Hey ma'am, I've also joined the lecture before.
I will check the attendance. I will come to know whether you joined first time or you joined and you got disconnected and all. On
Yes
time
ma'am,
you have
I've
to
joined
join
the
for lecture.
lecture and I disconnected.
Okay. So like this, the semaphore will work. Okay. Next, we have another solution, which is also a solution for mutual exclusion. But there, here the code segment, we have taken a code segment as a shareable segment. Okay, we have taken a code segment as a shareable segment. There is algorithm, that algorithm executed by all the processes. Okay, but here there is a buffer. Buffer is a memory. The next algorithm is called producer-consumer problem. Producer-consumer problem. After semaphore, binary and counting semaphore, we are going to see producer-consumer problem. Wait, I have working of this. I just open that. Wait. Okay. Next problem is called producer-consumer problem. But producer-consumer problem, there is a here these are shareable code segment we saw. Okay, but here we are going to see a buffer which is shared by more than one number of processes. Okay, but at a time only one process can use the buffer. Okay, there are two different category of processes which can access this buffer. One is called producer, another is called consumer. Okay, wait a second, students. Okay, students, look at the algorithm. In this algorithm also, weight and that weight function and the signal function is used. Okay. Assume that, look at the problem. Okay. So now there is a buffer. So this is a producer and a consumer. Producer and consumer can use this buffer. That means producer consumer means what? Is just to attract, they have kept the algorithm name as producer consumer. But this is a buffer a person can read and a person can write. Okay. But one is reading, another one should not write. Okay. So that this is sometimes called reader and read and write problem also. Okay. Can also be called producer consumer problem, popularly known as producer consumer problem. Okay. So there is a buffer can be accessed by producer process and also consumer process. Okay. We assume that the buffer size equal to 5. 1, 2, 3, 4, 5. There are 5 memory cells. Okay. 1, 2, 3, 4, 5. Okay. So buffer size equal to initially 5. Here we are using 3 variables, S, E, and F. S variable denotes semaphore, E denotes empty, F denotes full empty semaphore. Okay, to denote these 3 different things, we used 3 variables, which are S, E, F respectively. Okay. Initially, semaphore we are initializing with 1. Okay, semaphore 1. So here also semaphore is going to use this binary semaphore, either 0 or 1. Okay. S is semaphore variable. We are initializing value 1. E empty equal to 5. How empty equal to 5? Now look at all the 5 buffer. All the 5 buffer are currently initially it is empty. Okay. So empty equal to 5. Full equal to 0. None of the buffer is full. Okay. So full is 0. Empty, everything empty. So 5. Full, nothing is full. So 0 initially. Okay. Now assume that this is the algorithm. Producer starting to execute the algorithm. He has to execute weight of E. Okay. Always see this weight will be checking the semaphore value and decrementing the semaphore value by 1. Everywhere weight will do this only. Within the weight function, we will do only this. Okay. Within the weight function, always we will check the S value. If the S value is less than or equal to 0, it should be in busy weight. If it is this condition false, that means it is not 0 or less than 0, then the S value will be decremented by 1. Everywhere it is like that. Okay. So now here weight of E we are executing. Remember, not S, that is very important. Weight of E. Okay. So we have to execute this algorithm here by substituting E. Okay. Okay, weight of E. Now producer, students please listen. Producer is one of the processes. It is started to execute the algorithm. It started to execute weight of E. So here it is weight of E. So assume that in the place of S it is E. Okay. So weight of E, while E in the place of S you have to substitute E. E less than or equal to 0. E is what? What is the value of E? E equal to 5. Okay, E equal to 5. So 5 less than or equal to 0, the condition fail. Okay, the condition false. If the condition false, it will come inside. It will make here, wherever S comes, E. Okay, E equal to E minus 1, which means now currently E equal to 4. That's what here I have given. When weight of E is getting executed, E less than or equal to 0, it sees. The condition fails. When the condition fails, E equal to E minus 1, which is nothing but 4. Now currently remember E value equal to 4. Okay. Who did this? Who did this? Our producer process. Now producer process executed this. Okay. After executed E, he has to, after executed E only, it changed E equal to 4, remember. And then the producer should execute weight of S. Weight of S means it will come again here. Now S equal to S only. Okay. You know initial value of S, we initialized 1. Initial value 1, S equal to 1. So here what will happen? S less than or equal to 1. Here what will happen? 1 less than or equal to 0. No, condition fails. Again it will come here. S equal to S minus 1, which is nothing but S equal to 1 minus 1, 0. Okay. Look at here. S value 0. Who's executing all these? Producer executed E. Weight of E. By executing weight of E, it changed E value from 5 to 4. Okay. Then producer executed weight of S. By executing weight of S, producer changed S value from 1 to 0. Okay. This 2 producer executed. Now what it is doing, it is accessing the buffer. Which means it is a producer. So it is only allowed to add the item, not delete, remove. Removal cannot do. It cannot do. It can only add the item. Okay. That's why it is called a producer. Okay. So here the producer assume that it is entering one buffer. That means it filled buffer. Okay, one buffer it filled. Producer can produce, no? So it produced something. It stored something in first buffer. Okay. It's stored in buffer. Okay. So that I showed here. Add item. Who's adding item? Our P only. Producer adding item. After added the item, the buffer will be like this. Okay. Okay. Now assume that the process is adding item. That means producer is now inside the critical section. Inside the critical section, which is critical section here? This buffer. Buffer is a critical section. Okay. So producer is currently inside the buffer. Okay. Assume that another producer comes. Okay, another producer comes. It is executing weight of E. Weight of E now currently E is equal to what? Here you don't see, these are initial value. Now E equal to 4. Okay. Now 4 less than or equal to 0. 4 less than or equal to 0. This conditions now 4 less than or equal to 0. Condition will be false. Okay. It will come inside. Another producer can produce the item in another buffer. Producer can produce. Okay. Okay. Assume that when first producer, assume only one producer is inside. Producer produced item. Okay. When he is producing the item, that means when he is adding the item, assume that consumer process comes. Okay. Consumer process is executing because it wants to consume some item on the buffer. Okay. Consume is nothing but it wants to remove or delete or take it off from the buffer. That is consumer. Consumer can't produce anything, cannot add anything in the buffer. It can only remove items from the buffer. Okay. So consumer, it executes a weight of F. Okay, here I showed weight of F. Weight of F means here, what is F? F equal to currently, it is 0. Remember, F equal to 0, right? So F equal to 0. So it will come here. Weight of F, no? So it will come here. Here it is 0, less than or equal to 0, condition true. Okay. So consumer will be there in busy wait. Consumer will be there in a busy wait. Okay. When this consumer can consume, the item, a consumer is come now currently in busy wait. Assume that the producer went inside and produced a single item, no? He after produce, he has to execute signal of yes. Okay, currently you know signal equal to S equal to 0. Okay, producer only made S equal to 0. Okay, now S equal to 0, signal. So here this will be executed. So S will be simply incremented by 1. Now currently S equal to 1. Then the producer will execute signal of F. Okay, that is come here, that will come here. Now signal of F, initially F equal to 0. Okay, now F will be incremented by 1. F will be incremented by 1. What is now? Now F equal to 1. Okay, F equal to 1, S equal to 1, E equal to 4. Okay, S equal to 1, F equal to 1. Okay. Now look at the buffer. This now completely producer produced and came out of the loop. Okay. Now you look at the buffer. E equal to 4, yes. E equal to 1, 2, 3, 4, empty. Correct. F equal to 1, yes. Filled is only 1, so F equal to 1. Semaphore went to initial state. Initially, what is the state of the semaphore? 1. Okay. So S equal to 1. Now the signal, this is incremented, no? Because of F value only, the consumer could not enter inside the buffer. Okay. Now the consumer which was there in the busy wait will be released here because now F equal to what? F equal to 1. Condition fails. It will come inside. S equal to S equal to S minus 1. Now consumer is making S equal to 0. Consumer made S equal to 0. Okay. And then it is going inside the buffer and deleting the item. There is an item to delete, no? Because producer produced one item. So that item is consumed by this consumer. Okay. And after consumed, it will execute signal which will increment S by 1. So that is now currently S equal to 1. Then signal equal to E. Signal E means here, what is E? E equal to currently 4, no? Okay. Now E will become 5. Why? Because the only one filled item also deleted by the consumer. So now what should be the value? E will be 5, S equal to 1, F equal to 0. Okay. Simply what is the algorithm? If producer or consumer, before entering inside the critical section, two function it has to execute. If it is a producer, producer should execute the empty buffer. Okay. Because empty buffer here, empty buffer should not be 0. Okay. If empty buffer is 0, which means everything is filled. Everything is filled. So that time the producer cannot allow to add the item. Where it will add, some consumer should delete the item. Then only it can add the item. Okay. Then another one, both producer and consumer, before going inside the buffer, it is making the S value to 0. Okay. Making S value to 0. Okay. both the process after it did deletion or addition, adding the item or deleting the item in or to the buffer, it has to again reset the value, signal value to 1, because it made here 0, no, s equal to 0. It has to reset again s equal to 1, and the full should be depending on the action what it did. Suppose this is a producer. Producer added one item, so FMA1 will be incremented. Okay. Here in the consumer case, consumer will delete the item. So when he deletes empty May, 1 should be reduced. Okay. So these are the functions both should do. So this is the algorithm, which is called the producer-consumer algorithm. Okay. Here we segregated, here what actually we are doing, addition can be done by more number of processes if the buffers are empty. Okay. But at a time, one producer, when one producer is there, consumer cannot enter. When consumer is there, producer cannot enter. Okay. Why it is so? Why it is so? See, one producer is producing the item. Okay. At the same time, when you allow the consumer, there will be a race condition. Okay. Producer, whether he is on producing, because when he wants to produce, there are many things he has to execute. Wait of E, signal of S, signal of S, and all. So while it is executing any one of this, the consumer is allowed, there will be a race condition. Okay, there will be a race condition. For example, first process, it did not exactly add the item, but it is executing wait signal. Okay. So first process, wait signal, it is executing. Okay. It is seeing that empty is 5, so that it came here. It is successfully executing. Now on execution of yes. That time assume that consumer you are allowing. What will happen? Consumer, when he sees that full equal to 0, nothing got full. Okay. So he should not allow inside the buffer, because not the producer is on the process of producing. He has to produce, he has to complete the production, then only consumer can consume. Okay. Producer and consumer going at the same time, then the race condition will occur, because one is depending on another. Okay. Producer should complete the process, then only consumer can consume it. Okay. So output of the producer will be followed by or taken as an input for the consumer. Okay. So these are the dependent processes. This is a different scenario which will also implement the mutual exclusion, but inside the buffer. Inside the buffer. When one is writing, another cannot read. When one is reading, another cannot write. Okay. Because reading, writing happens at the same time, then there is a confusion. Suppose the content, content what I am reading. Just before I read. Oh, okay. Time is over. No.
Yes, ma'am. It's 12:40.
We have the next lecture at 12:40.
Also I do it today. Okay. Students, remember tomorrow 8 o'clock, morning 8 o'clock, operating system lecture. Okay. Remember, join exactly at 8. Okay. Thank you, students. You all can. Okay, students, you all can leave. Thank you.
Ma'am, what did you say? What will be tomorrow?
Tomorrow, as per the schedule, you don't have operating system lectures. Okay. But 8 o'clock, I will schedule the lecture. 8 to 8:50, one lecture, one operating system lecture, 8 o'clock. From 8 to 8:50, I will take tomorrow. Okay. And then followed by your other lectures. Okay. Yes, students, you all can leave.
Thank you.